This video is brought to you by Sc01 Group 2, and I will be discussing our DDW 2D project. For task 1, we used a multiple linear regression model to predict the number of deaths attributed to COVID-19 using predictor variables that gave the highest accuracy. The code here allows us to extract the specific data range in the data, thus creating a new data frame. The removed countries shown here are the same for task 1 and 2 when reading the CSV. Over here, we use .call to find the pairwise correlation of all columns in the data frame, with the specific method used being Pearson, which helps correlate the standard correlation coefficient. .call would then be utilized to plot the heat map, plotting all the variables according to its importance in the data. With the higher the value, the higher its significance. This is the heat map we've plotted, and these are all the columns of our data. Here I will give a brief run through of our functions and their purposes. The normalize z function is to normalize the inputted data frame's values with the formula as shown. The getFeatures function is to extract the stated columns as features of data and target of data. The prepareFeature function prepares the feature by converting the data frame into a numpy array, changing it into column vectors, and adding a column of constant ones. The prepareTarget function prepares the target by converting it into a numpy array. The predict function predicts y from y equals beta naught plus x times beta 1. The predict norm function matrix multiplies the two numpy arrays, in this case x and beta. The split data unrandom function splits the data's features and targets into training and test sets. Now to find the accuracy of the predicted data, we need to compute the error. The compute function is used for just that, to calculate the average error in n samples of data. Next, to predict the data from the base dataset, the gradient descent function is needed. It is an optimization algorithm that is used to minimize a function iteratively by moving in the direction of the steepest descent, as defined by the negative gradient, which finds the best fit line for a given training dataset in a smaller number of iterations while updating the parameter of our model. For the multiple linear regression function, we first removed the rows with missing values, extracted the features and targets as stated above, before normalizing the features of the dataset. We then displayed the features and targets as a summary of the columns, as well as plotting the features against the target. The data is then split using the split data function into train and test sets to prepare the variables needed for the next part. To evaluate our model, we then use three main parameters. The first parameter is the mean square error. The next parameter is the mean absolute error. And the final parameter used is the t-value. The variables that we have picked for our model are new cases, hospital patients, ICU patients, and weekly ICU admissions. To improve the model, we have selected the three most relevant factors, which are total cases, reproduction rate, and stringency index. After modeling the data, we get a better accuracy for the three variables as compared to the initial model. This better accuracy is shown by comparing the t-value for the initial model and improved model. The predictor section here allows the user to input their own values into the model and attempt to predict the value of new deaths with the input values. Now we will go on to task 2, where we will be analyzing the problem my group has identified and our solution to it. The main problem we have identified is caused by the scarcity of vaccinations. As such, we would like to evaluate the efficacy of vaccination rate, full vaccination against each other in predicting COVID-19 deaths. To do so, we examine their accuracy in predicting the total number of COVID deaths. As our solution, we build a linear regression model on each type of vaccination rate against the daily number of COVID deaths and use the accuracy of the model to determine which type of column generated the most accurate model. Our variables are hence defined as total vaccinations per 100, people vaccinated per 100, and people fully vaccinated per 100 against new deaths attributed to COVID-19. Finally, we deliberate on improvements, including ways to improve our accuracy. Using the same method stated before, we extracted the data from the CSV, plotted our heat map, and used the same functions for feature and target preparation. However, this time, we used a pair plot instead. This allows us to visualize relationships between each variable and produce a matrix of relationships between each variable in columns and new deaths in data. The regression function shown here is like the multiple linear regression function in task 1. There is no change in the core parts of the code. Using the regression function, we first plotted total vaccination doses administered per 100 people to the predicted new deaths. The second plot created was people vaccinated per 100 to the predicted new deaths. The third plot, people fully vaccinated per 100 to the predicted new deaths. We then used the accuracy checkers in task 1 to evaluate our plots. To improve our model, we drew inspiration from the multiple linear regression models used in task 1. The columns shown here are the columns that we decided to add to improve our model. The previous columns used in task 2 were then also added onto the list of columns in the columns variable. We will then use the accuracy checker to evaluate our model again. In task 2, we could also increase the data size, alter the proportion of tests and training sets, and examine ways in which the factors are correlated to improve accuracy. From these values, we can now determine the magnitude of the error. This allows us to identify that the multiple linear regression model's best variables are total vaccinations per 100, total cases, reproduction rate, and stringency index. Consequently, we can then determine which governmental policy on vaccination should be advocated based on the stage of the pandemic.
My name is Jobal, and I'll be going through on how you can use our COVID-19 data dashboard. For the first feature, we have a global summary where users can plot the chosen x-axis data against the y-axis data from all countries. In this case, you can see that the new cases are being plotted against the new deaths for all countries. These columns can also be changed. The next feature that I'll be introducing is the national summary. Users can plot the chosen x-axis data against the y-axis data for a specific country. This is similar to the global summary, just that it has been narrowed down to a specific country. In this case, new cases has been plotted against new deaths for Singapore. This can be changed. So can the columns be changed. Another feature that we have is the global by date feature. Users can plot the chosen x-axis data against the y-axis data from all countries of a certain time period. In this case, new cases and new deaths have been plotted for the 25th of November. This can be changed. The fourth feature that we have, national by date, allows users to plot the chosen x-axis data against the y-axis data using data from a specific country of a certain time period. This is similar to global by date, just that you can change it to different countries. Another feature that we have is the linear regression feature. In the linear regression feature, user can predict the y-axis values given the x-axis data. The data is then plotted against for both the actual and predicted y value against the x value used. An accuracy table has also been provided to tell you the accuracy of your predictions. The final feature that we have is the predictor function. And the predictor function is able to predict the number of new deaths given the total number of cases, reproduction rate, and stringency index of the country for a particular day.